Good morning. This is Unlock Circuits 18EC42 Module 2, Lecture 1, Part 2, MOSFET Amplifier Configuration. I'm Dr. Nurullah Sharif C, Professor at Head, ECAV Institute of Engineering and Technology, Vijaypura. In the last class, we have seen the three basic configurations of the MOSFET: common source amplifier, common gate amplifier, and common drain amplifier or source follower. We also tried to characterize the amplifier. And then we have seen the common source amplifier. Now, today we will see the common source amplifier with source resistance and also the common collector, or what is known as the source follower. Now, if you see here the common source amplifier with source resistance, then the difference between this figure and the earlier figure is the addition of the source resistance Rs over here. So you can just see in this, there is no Rs over here, whereas there is Rs over here. So if you add Rs over here, what is the effect of this Rs on the different values of Ri, R0, and AV, in particular the AV, AV0, AV, and GV, then we will see in this class. So now what we are trying to do here is the MOSFET here is replaced by its T model. Its T model, wherein the I, this is a dependent source, which is I, and you have the resistance, which is written as 1 by the transconductance value over here, and the rest of the thing, R sig, V sig, RS, RD, all remain same. Again, we have not added the load resistance RL to it. If you want, you can always include the load resistance RL to it, which will come naturally in parallel with RD. So this is with the consideration that we have open circuit voltage gain, which we are trying to measure, and if we consider the normal gain, then RL will come here, and that will come in parallel with RD. Then RD can be just replaced by RD in parallel with RL. Now, the input resistance again for the MOSFET is infinite. The input resistance of the MOSFET is infinite. Therefore, the current which is entering the MOSFET is always equal to 0. And because the input impedance is infinite for the MOSFET, for the overall CS amplifier with source resistance, again, the input impedance will be infinite. Because of the same thing, we see that the value of Vi will also be same as the Vc itself, because Rin is infinite. So Vi will be equal to Rin divided by Rin plus R sig multiplied by V sig. Already in the last class, we have seen this in the characterization of amplifier. And because Rn is infinite, in the limiting case, Rn divided by Rn plus R sig will become equal to 1, and hence the value of Vi will be equal to V sig. Now, we want to find the relationship between the the equation for the output voltage. So first we need to find out the relationship between the Vi and VGS, and from that we can always find the V0. Otherwise also, I think it's not needed for us to find out that. So here the V0 is equal to IRD. You can see here that V0, which is measured across this, is same I is flowing through the resistance RD, and hence the value of V0 will be rather minus IRD. Minus IRD. So V0 will be equal to minus IRD, because the direction of the current which is flowing through the RD resistance is from here to this, like this. So now we can find the value of the I there. So I can be found over here, which is something like this. This is Vi. Vi is between this point and the ground. So I will be Vi divided by 1 plus Gm plus Rs. And the same thing is being mentioned over here. I is equal to Vi by 1 plus Gm plus Rs. And that can be written as Gm by 1 plus Gm Rs into Vi. So the value of I is equal to this. So that can be substituted over here so that we will get V naught is equal to Gm plus 1 plus Gm Rs into Vi multiplied by Rd. So definitely V naught by Vi, that means Vi if you take on the other side, that means on the left hand side, then we'll get V naught by Vi is equal to minus Gm Rd divided by 1 plus Gm Rs. And that is what is mentioned over here. And the same thing can also be written as Rd by 1 plus Gm into Rs. So the open circuit voltage gain, we have found it to be minus Gm Rd by 1 plus Gm Rs. Output resistance, naturally in the earlier circuit over here, looking from here, the output resistance will be Rd itself, and the voltage gain of the amplifier proper, which is known as AV, will be, as I already said, that Rd has to be replaced by Rd in parallel with RL, because RL also will be coming into picture in the what we call voltage gain of the amplifier proper, which is known as AV. So you can just say that AV is equal to minus Gm Rd in parallel with RL divided by 1 plus Gm Rs. Or other way spoken, you can write AV as AV naught multiplied by RL divided by RL plus R naught. Again, if you replace the AV naught by this quantity, then you will have in place of Rd multiplied by RL divided by RL plus R naught, and that is naturally Rd in parallel with RL. The overall voltage gain GV will be equal to AV, because again we have the Rn equal to infinity. The value, the formula for GV and AV is GV is equal to AV into Rn divided by Rn plus the R sig, and in the Rn is nothing but infinity, infinity by infinity plus Rs, and in the limiting case Rn divided by Rn plus Rs will be equal to 1, and therefore GV will be equal to AV. So summarizing the what you call CS amplifier with source resistance, we can just say that the input resistance Rn is infinite. Open circuit voltage gain AV is reduced by a factor which is 1 plus GMRS compared to the common source amplifier without the source resistance. And for the same nonlinear distortion, we can say that the input signal can be increased by a factor 1 plus GMRS compared to without RS. So we can increase the input signal by this amount for same amount of linear distortion when we are using RS compared to without using the RS. And we also see that the high frequency response of the common source amplifier with source will be better, and this we'll see later. In general, the addition of the source resistance Rs gives rise to negative feedback factor, and this 1 plus GMRS can be considered as a negative feedback factor that reduces the voltage gain but improves the linearity, and as well it improves the high frequency response. And because of this negative feedback action of RS, it is also known as the source degenerative resistance. So RS provides negative feedback, and this improves the performance of the device in terms of the high frequency response and also linearity. Further to this, the formula for AV naught is mentioned over here, where it is minus Gm Rd divided by 1 plus Gm Rs. So this was the value without Rs, and with Rs we are dividing that by 1 plus Gm Rs, and that's what is specified here. Now let us see what is the need of a unity gain amplifier. Why do we need a unity gain amplifier at all? So in a normal picture, when we have a load resistance over here and the source is connected to that like this, then if the value of R sig is 1 mega ohm and RL is 1 kilo ohm and V sig is 1 volt, then naturally the value of the voltage at the output, which is across the RL, will be approximately equal to 1 millivolt. Exactly if you talk, then it will be V naught is equal to RL divided by RL plus R sig multiplied by the V sig. So RL will be 1 kilo ohm, RL plus R sig will be 1 mega ohm plus 1 kilo ohm multiplied by 1 volt, which is approximately equal to 1 millivolt. So you can see that directly connecting the load to the source just gives us a very large reduction in the output compared to the input. The input is 1 volt, the output is 1 millivolt. So this is the loading effect. This is basically known as the loading effect which occurs, and this reduces the voltage to 1 millivolt, output voltage to 1 millivolt compared to 1 volt. And thus we need to have, to reduce this loading effect, we need to have a unity gain amplifier. So if you connect, say, a unity gain amplifier over here, then what's it which is going to happen? Now, the unity gain amplifier, which is the MOSFET based one, has the input impedance of this to be infinite, or you can say very, very large, might be hundreds of mega ohms, or ideally speaking, you can consider it as infinite. An ideal, unity gain amplifier is supposed to have the infinite input impedance and output impedance, which is very, very small. So because the input impedance is, almost infinity or very large compared to the R sig, we see that the pole of the V sig appears at the input terminal. That means we will have V sig, the input voltage to be equal to 1 volt, which is same as V sig, because the what you call input resistance is infinite. You can say that Vi is equal to Rn divided by Rn plus R sig into V sig. And because R sig is very small compared to Rn, in the limiting case, Rn divided by Rn plus R sig will be equal to 1. And hence, the value here is 1 volt itself, whatever we have here. Similarly, in the same way, we have here 100 volts as the output impedance of this op amp. And this 1 volt amplified will give us 1 volt at this point, and then you have the R0 resistance over here, and the value of 1 volt will get distributed between the 100 ohms and 1 kilo ohm, and that will give us the output voltage. So output voltage will be this value of Vi multiplied by RL divided by RL plus R0. So that will be naturally 1 kilo ohm divided by 1 kilo ohm plus 100 ohms, and that will be 1.1 kilo ohm. So 1 kilo ohm divided by 1.1 kilo ohms into 1 volt will approximately be the 0.9 volts. So thus, if you have a unity gain amplifier, a ideal or a good unity gain amplifier over here, then the output will be reduced very less compared to the input. Whereas if we don't use a unity gain amplifier, then the loading effect will create havoc, and that will reduce the output to a very small, meager value compared to the input. Thus, the need of the unity gain amplifier, which is provided by the common drain amplifier, or what is known as the source follower. So now you can see that we have put here a common drain amplifier or source follower, and we're taking the output across actually at the source, between the source and the ground where the RL is placed over here. Again, we are replacing the MOSFET by means of the T model over here. From this, we can try to find out what is the value of the input voltage, what is the value of the output voltage, input resistance and output resistance, and AV0, AV, and GB. So Rn is infinite again, and R0 is equal to what we call R0 will be the value wherein we need to ground the input side, and then 1 by GM is the one which is going to come in parallel with RL, and 1 by GM is much smaller, and hence R0 will be equal to 1 by GM itself. Or you can, if you want to be more accurate, then R0 can be 1 by GM in parallel with RL. But if you consider only the transistor, then it will be 1 by GM. So input resistance is infinite, and the R naught is 1 by GM without considering the RL. The what you call voltage gain proper, which is AV equal to V naught by VI, considering the RL itself, you can try to find out V naught is the voltage across RL. V naught is the voltage across RL, that is I into RL, and VI is the voltage across 1 plus GM plus RL, that is I into 1 plus GM plus RL. So we are going to get the value of the AV to be equal to RL divided by 1 plus GM plus RL, and uh, that will be the equivalent value of that will be RL divided by RL plus 1 by GM, and this value is approximately equal to 1 because of the reason that 1 by GM is much smaller than RL, and hence you can neglect this, and then we'll get RL by RL is equal to 1. So AV naught is approximately equal to 1. Also, the overall voltage gain GV will be equal to AV because Rn is infinite. GV is equal to AV into Rn divided by Rn plus R sig, and in the limiting case, Rn divided by Rn plus R sig will turn out to be equal to 1, and hence GV will be equal to AV, and that will give you RL divided by RL plus 1 by GM, which is mentioned over here. So this table gives us the summary of the uh, performance of the different configurations of the MOSFET, common source with resistance RS, and the source follower, and as well as the common gate amplifier, which is out of the scope of the syllabus, and that is because the common gate is seldom used because of its very poor performance. You can see that the input resistance of the common gate amplifier is just 1 by GM compared to the infinity. We would like to have infinite input impedance, and we would like to have as low output impedance as possible. And here we have 1 by GM, very low output impedance. Here we have RD in all these three cases. So as far as output impedance is concerned, the source follower acts very well, converting a high input impedance into a low output impedance. The common source amplifier has a very good amplification compared to the others. So you have here minus GMRD, and the common source amplifier with RS is this, and that provides the reduction of the AV naught, AV, and GV by the same factor 1 plus GMRS, and that is provided by the negative feedback due to RS. So summarizing and comparing the MOSFET with the BJT, we can say MOSFET amplifiers have high input impedance compared to with the BJT, except for the CG amplifier. BJTs have higher conductance GM than MOSFETs, giving BJT amplifiers higher gains. Discrete circuit amplifiers, example circuits assembled on printed circuit boards. For that, we have BJTs are more prudent because of their longer history and wider commercial availability. Because of easier fabrication, we see that in the integrated circuit amplifiers, the MOSFET are the dominant technology. The common source and the common emitter configurations are best suited for amplifiers which should provide gain because of their larger gain than the unity gain. A cascade of them can be used to increase the gain. You can connect two or more of the CS amplifiers or the C configuration amplifiers to get more gain. The addition of RS in the CS amplifier or the RE in the CE amplifier improves the linearity of the circuit by providing negative feedback, and that increases the high frequency performance as well. So we have here a question: what is the basic difference between the MOSFET amplifier from the BJT amplifier? Whether it is low input impedance, whether it is the high or the infinite input impedance, or it is none of the above. Naturally, the MOSFET has high input impedance compared to the BJT amplifier. In the ideal case, we generally consider the input impedance of the MOSFET to be equal to infinite. With this, we come to the end of the